Last lecture we have seen up to equation of normal, auxiliary equation, and then we have seen a special property that eccentric angles of co-normal points add up to odd multiple of 180. Let us do geometric properties of ellipse. First, SP plus S dash P is equal to 2. Sum of focal distances is constant, equal to, we have already proved this, SP was A minus EX1 and S dash P was A plus EX1, made it equal to. That means if you happen to have ellipse, this is S1, S and S dash, you take any point on ellipse, the distance traveled from S to S1 after touching the ellipse is going to be the same. No problem at that point. No. I mean, you can choose any point on ellipse. SP plus S dash P is always equal to length of major axis. Property number 2. The normal at P bisects angle between focal radii. So this is your y-axis, and if you draw normal at P, this is tangent at P, and if you draw normal at P, it bisects the angle. This angle is equal to this. Prove this. You can take ellipse, standard ellipse, x square upon a square plus y square upon b square is equal to 1. This is our standard ellipse. And prove that normal bisects the angle between focal radii. Very important property. Okay, let Px dash y dash be the point on the ellipse. Then equation of tangent is x dash upon a square plus y dash upon b square is equal to 1. Now this, what am I doing? Focal radii. So equation of normal a square x upon x dash minus b square y upon y dash is equal to a square minus b square.
Sir,
Yes.
if we prove the normal is angle bisector of them, it means the normal also, right?
It means
The normal also an angle bisector, right?
not understood.
So we have P and some. So the normal is angle bisector of the focal radii.
Yes, angle bisector of S angle SPS dash.
So like won't the tangent be also the
exterior angle bisector.
yes.
Yes,
So if we prove like that, then
it is okay. You can prove either of the two. Either normal is internal angle bisector or tangent is external, one and the same. So if this is equation of normal, it intersects x-axis and that point is called G. The coordinates of G is we have to put y is equal to 0 and therefore x coordinate comes out to be a square minus b square upon a square into x dash and y coordinate is 0. Okay, so you can find out distance s dash g upon gs and you know ps dash upon ps and you should get that bisect. You do that those calculations. I don't know why you have taken so much time, but anyway. Problem number 3. Now, before, okay, this is tangent, let me call P dash. Prove that tangent to circle at P dash tangent to auxiliary circle at P dash to ellipse at P and x-axis are concurrent. Okay, point P, if we write parametric, then it is a cos theta comma b sin theta, and P dash parametric if we write a cos theta comma a sin theta. Okay, and the equation of circle is x square plus y square is equal to a square. Therefore, equation of tangent to of circle is x a cos theta plus y a sin theta is equal to a square, which is x cos theta plus y sin theta is equal to a. We could have directly written this. Now, if we solve this simultaneously with x-axis y is equal to 0, you end up getting x is equal to a by cos theta. Okay, and y is equal to 0. So this point must lie on the tangent of ellipse, which is a cos theta x upon a square plus b sin theta y upon b square is equal to 1, which is, I substitute this back and it is a gone, x is equal to a by cos theta, so 1 plus something into y is equal to 1. Therefore, y must be 0. Y must be 0 and hence they are concurrent. Okay. One important information about first two properties. See now, first property says if I start from S, touch ellipse at any point P and go back to S dash, I will travel exactly same distance no matter where I touch. On the surface of ellipse, on the curve of ellipse, wherever I choose point P, touch and go back in the straight line, I will travel exactly to a distance. Moreover, if the ellipse is a mirror, then ray from S from S will get reflected at the surface of the ellipse and will pass through S dash. So, say for example, if there is a sound created at S, then that sound will reach at S dash exactly after some specific time, no matter whether it is getting reflected like this, or it is reflected like this, or it is reflected like this. Okay, that is very important. If you happen to visit Raigad, महाराजांचा जो दरबार होता त्याच्यात महाराज इथे बसायचे फोकसवर आणि इट वॉज द वॉल्स वेर इलिप्टिकल and it is big, it is not small. Walls were elliptical, and therefore if somebody is talking in a very low voice at this point, because of the property of the ellipse, the distance traveled is same and it is reflected. Therefore, even if you can go and test it, even if you talk in very low voice at this point, it is clearly heard here, clearly heard. That is the application of this property of ellipse. Okay. Now, referring to this diagram, property number 4. Okay, what is this diagram? Let me explain. At P, I have drawn tangent which intersects x-axis at capital T, y-axis at small t. We have drawn normal which intersects x-axis at G and y-axis at small g. Pn, n is a foot of perpendicular from P on x-axis, capital N, and small n y-axis. And C, if I drop perpendicular on the normal, it is small f. This is the notation. So if this is true, then prove that, or Cn into Ct is equal to a square is equal to Pf into Pg. Cn into Ct is equal to small a square. I mean, this is easy. Cpt. Cn into Ct is equal to small a square, because this is 90 degree here. This is 90 degree. Complete Pythagoras theorem, first part. However, a square is also equal to Pf into Pg. Pf into Pg. Do this. I mean, every identity that I am going to give you now can be done in two ways. One, coordinate geometry, and two, geometry. You try both. I give you sufficient time to try both, but first finish by coordinate geometry so that you are sure that this is working, and then we can put our energy in doing some additional constructions, etc., so that if we could prove it geometrically, it gives us pleasure.